Dear students, I am Mahesh Javalkar of Maratha Mandal Polytechnic, and today I am posting my second video on analog electronic circuits subject, in which I am going to cover rectifiers, ripple factor, efficiency. Okay, so let's start with the presentation. So in this presentation, I'm going to tell you what is a rectifier, a classification of rectifiers, define ripple factor of rectifier, define efficiency of rectifier, ripple factor of half wave rectifier and full wave rectifier, efficiency of half wave rectifier and full wave rectifier, and a comparison of rectifiers. Okay, so let's start with what is a rectifier. Okay, now basically, if you see, a rectifier is a circuit which converts AC voltage into a pulsating DC voltage. Okay, so AC voltage is converted into pulsating DC voltage. So here, if you see, if you draw the AC voltage will be like this. It will be having positive half cycle, negative half cycle, positive half cycle, negative half cycle. Okay, so this should be converted into a unidirectional. In half wave rectifier, it will be only positive half cycles, but in full wave rectifier, it will be positive half cycles for every input. Even if the input is negative half cycle, the output will be positive half cycle. So these are unidirectional flows. These are unidirectional. Unidirectional. Okay, that means it is in one direction. Okay, it is not alternating quantity, it is not bidirectional. Okay, so these are called as pulsating DC because it is not a pure DC. It is a DC, but it is not pure DC because it has AC component in it, which is called as ripple. Okay, so here basically when we define what is a rectifier, rectifier is a circuit which converts AC voltage into a pulsating DC. Pulsating because it will have some AC component. So it is not pure DC, it is pulsating DC. Okay. So AC voltage converted into pulsating DC voltage is done by a rectifier. Then if you see the classification of rectifiers, there are three types. The first one is called as half wave rectifier, which consists of one semiconductor diode. Second one is called as full wave center tap rectifier, which consists of two semiconductor diodes. And third one is called as full wave bridge rectifier, which consists of four semiconductor diodes. Okay. Then if you see the definition of ripple factor, ripple is the content, AC content in the output of rectifier DC. Okay. So output of rectifier should be a DC, but that DC will consist of some AC component, which is called as ripple factor. Okay. Now, if you want to define ripple factor, a ripple factor is defined as the ratio of AC voltage at the output to that of the DC voltage at the output. Okay, so it is AC voltage at the output or DC voltage at the output. You can define it in terms of current also. So here below we have given the definition in terms of expression. So here you can see ripple factor RF is equal to IRMS, which is AC quantity, upon IDC, which is DC quantity. Okay, so AC current upon DC current at the output is called as ripple. Similarly, in terms of voltage also you can give it here. So you can see here ripple factor is equal to VRMS, that is VAC, AC quantity of voltage upon DC quantity of voltage. Okay, so if you take the ratio of AC voltage at the output to that DC voltage at the output is called as ripple factor. So basically it is the AC component present in the pulsating DC output of the rectifier. Clear? So that is called as ripple factor. Similarly, if you see the expression exact for a ripple factor will be given as RMS value of AC component of output to the average value or DC component of output. This is a general expression for ripple factor. Clear? Then if you see what is ripple frequency, okay, it is the frequency of the output signal of the rectifier. Okay, now frequency is number of cycles per second. Okay, so input will be a AC, and in every AC there will be a positive half cycle, negative half cycle, positive half cycle, negative half cycle. Positive and negative together will become one cycle, and number of such cycles in 1 second is called as frequency. Okay, so it is the frequency. Now here he has asked what is ripple frequency. So ripple frequency is the frequency of the output signal of the rectifier. So whatever rectifier's output you will get, and the frequency of that output signal is called as ripple frequency. Okay, it is defined as the vibration of the pulsating DC signal in number of cycles per second, or it is also called as hertz. Hertz is a unit of frequency. Okay, for half wave rectifier, ripple frequency, that is FR, is equal to F. F is the original frequency, and in full wave rectifier, FR is equal to 2F, that is twice the original frequency. Okay, at the input. That means FR is equal to F for half wave rectifier, and FR is equal to 2F for full wave rectifier. Then we'll go to see efficiency of a rectifier. Okay, what is the efficiency? How much DC power it is going to give at the output as compared to the AC input. So here the definition says that the rectifier efficiency, okay, it is given in eta, is defined as the ratio of output DC power given to the load, delivered to the load, to the input AC power from the transformer. So here the input will be taken from the transformer, and output will be given to the load as far as the rectifier is concerned. Now, whatever rectifier you are having, that output DC power to input AC power. So say for example, you have shown a block of a rectifier here. So this is a block of a rectifier. Okay. So the input will come from the transformer. Input will come from the transformer. This is rectifier, and output will go to the load. This will go to the load. This will come from the transformer. Okay. So now here DC power delivered to the load, PDC. Okay, to the input AC power, PAC, input AC power. Okay, that ratio if you take, it is called as efficiency. So efficiency will be equal to PDC upon PAC. This is your efficiency. Eta is equal to. Clear? So below here we have given the expression efficiency is equal to. So here you can see efficiency will be equal to DC output power upon AC input power. Okay. Similarly, you can write it as PDC upon PAC. Efficiency is equal to PDC upon PAC. Next, we'll go to see what do we mean by peak inverse voltage, PIV. Now, it is the maximum voltage the diode must withstand during negative half cycle of the input. Okay, that means whenever the input is negative half cycle, what is the maximum voltage the diode can withstand? So if you see in the first case, peak inverse voltage for half wave rectifier is given as the maximum amplitude of the voltage Vm. In the second case, peak inverse voltage for full wave rectifier center tap, which is equal to 2 Vm. And in the third case, peak inverse voltage in full wave rectifier for bridge type, it is Vm. Okay, so for half wave, it is Vm. For full wave center tap, it is 2 Vm. And for full wave bridge rectifier, it is Vm. Okay, then we'll go to the next rectifier circuits. Then what is a half wave rectifier? A half wave rectifier is defined as a type of rectifier that only allows one half cycle of an AC voltage waveform to pass, and it blocks the other half cycle. Okay, usually it passes the positive half cycle and it blocks the negative half cycle. Half wave rectifier are used to convert AC voltage to DC voltage and only require a single diode to construct. Okay, so here you can see if the input is like this, if the input is say alternating quantity, plus cycle minus cycle, plus cycle minus cycle. Okay, then the output of half wave rectifier, for every plus cycle you will get an output, but for minus cycle there is no output. Then for another next positive half cycle of the input, you will get a positive half cycle at the output. So only the positive half cycles will be delivered at the output, and the negative half cycles will not be delivered, because at that time the diode will be reverse biased. So this is called as half wave rectification. A full wave means what? Plus and minus cycle both should be rectified. But in half wave, only half cycle is rectified. Another half is not passed. Okay. So here if you see, a simple diode is shown, and you see that the input is negative half cycle and positive half cycle both. So here you can see the input. This will be the input. Okay. And in this you will be having positive half cycle, negative half cycle, positive half cycle, negative half cycle. When it passes through the diode here, when it passes through the diode here, this is a diode. Okay. This is a diode. So whenever the input is positive half cycle, you will get the output as positive half cycle. But whenever the input is negative half cycle, the diode is reverse bias and it will not get any output. Okay. Similarly, when the next positive half cycle comes, again a positive half cycle will come at the output. So only when the inputs are positive half cycles, you are going to get the output. Whereas when the input is negative half cycle, the diode will be reverse bias and it will not conduct, and there will be no current at the output. So this is a simple diode functioning what we have shown. This can be converted into a circuit like this. You have an input voltage here, input voltage which is called as supply, input voltage which is called as supply V. So here you can have this input which is an alternating quantity. Okay, and then here you are having primary of the transformer. This is primary coil of the transformer. This is secondary coil of the transformer, and secondary is given to the diode, and then diode will see that across this load you will get only the positive half cycles, only the positive half cycles. Okay, plus and plus, this is plus, this is plus. Negative half cycle you are not going to conduct. This will be the circuit what is shown for a half wave rectifier using step down transformer. Similarly, if you complete the circuit like this with the waveforms, you can see that the input is a AC, plus minus is there. It is given at the input over here. So here you are going to give the input. This is the input. Okay. When the input is given to the primary of the transformer with mutual induction, it will be stepped down in terms of voltage and given to the secondary. Secondary will be applied to the diode here, and diode will conduct only when the input is positive half cycle, and when the input is negative half cycle it is not going to conduct. Therefore output will be only positive half cycles. So it is half wave rectification, it is not full wave. It is going to conduct only for half waves. Then we'll go to see what do you mean by center tap full wave rectifier. Now, in case of center tap full wave rectifier, only two diodes are used, okay, and are connected to the opposite ends of a center tapped secondary transformer. So a center tap transformer is used here. Okay, so with two diodes, we are using a center tap transformer. And there, if you see the diagram here, you can see the input is given as an input AC signal with positive and negative half cycles. So here you can see the input. This is the input. Okay, so you are having positive and negative half cycle. So when the input is positive, this point A will be positive. This point A will be positive. Diode D1 will conduct and the current will flow from here to the load to the center point. This is the center point of the secondary of transformer. Okay. Similarly, when the input is negative, the point B will be positive and here will be your negative. So the current will flow like this. Diode D2 will conduct and it will go to the load and come back to the center point. Okay. So in this way, across the load resistance, you can see the flow of current will be in this direction only. Even on the top it is really in this direction, and even down it is in this direction. So it is unidirectional. So for every half cycle, whether the half cycle input is positive or negative, you will get a output positive half cycle. Okay, that means it is full wave rectification. The rectifier is going to rectify the positive half cycle also and negative half cycle also. So it is called as full wave rectification. This is called as center tap because you are using a transformer which is center tap, and using two diodes for rectification, you can get this center tap full wave rectifier. Then we'll go to see what is a full wave bridge rectifier. Now to rectify both half cycles of a sine wave, the bridge rectifier uses four diodes connected together in a bridge configuration. Okay, so there is a bridge which is built because of four diodes. The secondary winding of the transformer is connected on one side of the diode bridge and the load on the other side. Okay, so if you see the diagram here, you can see this diagram here. So input is applied over here. So here you are going to apply the input AC AC signal input AC. Okay, which will be your positive negative half cycles. So this is plus minus plus minus. This is what you're going to apply here. Now, when the input is positive half cycle, this point is positive, diode D1 will conduct and the current will flow through the load like this. Okay. And then it will come here, it will come here, it will come here, and then D2 will get conducted and will come back to the negative point. Okay, so here negative point will be there. Okay, so in the first case, when the input is positive half cycle, D1 and D2 will get conducted. Similarly, when the input is negative half cycle, when this is positive, okay, so it will be D3 which will conduct, and the flow of current will be like this, and this will go here. Okay, this will go here. Through D4 it will come out. Okay, so D3 and D4 will conduct when the input is negative half cycle. D1 D2 will conduct when the input is positive half cycle. That means two diodes will be used at each time to convert one half cycle into a positive half cycle at the output. So if you see the complete diagram here, the input is applied here, input is applied to the transformer. So here you can see the input. Okay, so here you can see the input which is called as V in, and then input is applied to the transformer, and in input we have shown the AC half cycle and AC positive half cycle and AC negative half cycle. So here you can see AC positive half cycle and AC negative half cycle. This is the input. Okay, this is the input. So it is applied to the primary of the transformer. Now that is given to the secondary of the hot transformer, and after the secondary of the transformer, you are having a bridge circuit here. Bridge circuit is given here. Okay. So when the input is positive half cycle, that means this point will be positive. The top point will be positive here. So this is positive. So once this is positive, the current is going to flow through diode D1, then it will going to flow through the load. Okay, then through the load it will come to this ground point, and then it will come here. Okay, and through D2 it will go back to the down point of the transformer. Okay, similarly when the input is negative half cycle, okay, when the input is negative half cycle, this will be negative, this will be positive. At that time the D4 will be conducted, it will go down here to the this thing negative ground, and then from here it will come and D3 will be conducted and it will go to the top point. Okay, that means whenever the input is positive half cycle, D1 and D2 are going to conduct, and whenever input is negative half cycle, D3 and D4 are going to conduct. So if you see the input as positive negative, so here you can see the output as for positive input the output is positive, and for negative input also the output is positive. That means it is going to convert for the full, that is both half cycles will be converted into positive half cycles at the output. So it is called as full wave rectifier, and because you are using a four diode bridge, it is called as full wave bridge rectifier. Okay, then we'll go to see what do you mean by ripple factor of half wave rectifier. Now for half wave rectifier, we know now these two equations you should remember. IRMS is equal to Im by 2. So this is the first equation. IRMS is equal to Im by 2. Okay. Im is the maximum current upon 2 will be IRMS. Similarly, IDC will be Im by pi. This will be your second equation. Im by pi. Okay. Now you take the formula for ripple factor. Ripple factor is equal to under root. So here we have shown root. This is under root. So here this is under root. This complete is under root IRMS upon IDC whole square minus 1. Okay. So here you substitute the value of equation 1 and 2. So this you can call it as equation 3. So in equation 3, you substitute the value of equation 1 and 2. If you substitute that, you will get ripple factor as equal to 1.21. So here you can see 1.21 will be the value of ripple factor in half wave rectifier. Okay. So the ripple factor is more in half wave rectifier. The conversion of AC to DC is little less in half wave rectifier. Okay. Similarly, if you see ripple factor for full wave rectifier, then first we have to start that IRMS, IRMS that is root mean square is given as, so here you can have this equation number 1, Im by root 2, and similarly IDC, that is the DC current will be 2 Im by pi. Okay. Now the formula for ripple factor will be this equation 3. Now, if you substitute equation 1 and 2 in equation 3, we'll get the ripple factor of full wave rectifier as 0.48. These values you have to remember. Okay. So earlier we saw our ripple factor for half wave rectifier, it was 1.21. And now we are seeing ripple factor for full wave rectifier, it is 0.48. So it is exactly half of what we had for half wave rectifier. Then we'll go to see efficiency of half wave rectifier. So here you can see for half wave rectifier, as we have taken earlier also, IRMS is equal to Im by 2. IRMS is equal to Im by 2. This is equation number 1. This is equation number 1. And IDC is equal to Im by pi, equation number 2. And efficiency is given by DC power upon AC power. Okay. So if you substitute DC power as I square DC into RL, this is what you can see here. This is nothing but I square DC into RL. This is your DC power. Similarly, if you see what is AC power, so AC power is I RMS square into, okay, diode resistance plus load resistance. Okay, diode resistance plus load resistance. Now, if you substitute these values for PDC and PAC, and if you take the ratio of PDC upon PAC, then we will get the efficiency of half wave rectifier as 40.6%. So here you can see we have given the efficiency as 40.6%. Similarly, if you go to see efficiency of full wave rectifier, so for full wave rectifier, you can see equation number 1, IRMS is equal to Im by root 2. So here we have given the first equation, IRMS is equal to Im by root 2, and IDC is equal to 2 Im by pi. Okay, and same we will take efficiency is equal to, efficiency will be equal to PDC upon PAC, and here we'll take PDC as I square DC into RL, and here we'll take PAC as I square RMS into diode resistance plus load resistance. And if you substitute those values, PDC upon PAC, you will get the efficiency of full wave rectifier will be 81.2%. Now this will be more as compared to half wave rectifier efficiency. If you see half wave rectifier, it was 40.6% efficiency, means that much conversion from AC to DC was done. And if you see the full wave, it is 81.2. So here the efficiency will be more as compared to half wave rectifier. Okay. Then if you compare the rectifiers, so we'll take the parameters on the first line, then half wave rectifier, full wave center tap, and full wave bridge type. Okay. So if you take the first parameter, number of diodes, in half wave rectifier, we know that we have used only one diode. In full wave center tap, we are using a center tap transformer with two diodes. And in full wave bridge, we are using a bridge of four diodes. Okay. Similarly, if you see the second parameter, that is peak inverse voltage for half wave rectifier is Vm, and for full wave center tap rectifier is 2 Vm, and for bridge it is Vm. Okay. Similarly, if you see a ripple factor for half wave rectifier is 1.21. For full wave rectifier center tap it is 0.482, and for full wave bridge also it is 0.482. Similarly, if you see efficiency, it will be 40.6% for half wave rectifier, 81.2 and 81.2 for both full wave rectifier. Similarly, if you see ripple frequency, it will be F for half wave rectifier, it will be 2F and 2F for the full wave rectifiers. Similarly, if you see the sixth point of transformer necessity, there is no require of transformer for half wave rectifier. It is a simple one diode circuit. So if you don't use transformer also, it's okay. In center tap, you require a transformer because it is based on center tap secondary transformer only. And in bridge also, there is no need for you to use transformer. Okay. So these are some 6 important points where we have compared for rectifiers. Okay, students, now this was the explanation on rectifiers, ripple factor, and efficiency for half wave rectifier and full wave rectifier. What is there in your analog electronic circuit subject? If you are having any doubts, you can ask me, or you can send a feedback, or you can send a comment below my video so that I can answer your question. Okay, thank you very much.